All right, so we are going to do separable differential equations. So what is that? So let's start with what a differential equation is. So I'm going to give you some examples. So one example might be something like this. Well, you got to pick pen for it to work. dy dx equals 3y, all right? Why is that considered a differential equation? Well, because it's an equation, has an equal sign in it, and it has a derivative in it. So we call it a derivative equation or a differential equation, all right? Pretty simple. You can see it in this notation versus you can see it in prime notation. So the equivalent differential equation over here would be y prime equals 3y. Those are both differential equations, all right? We could have something like this. We could have 2 dy dx plus, say, x equaled 2y plus 1, right? This is a differential equation, again, because it has an equal sign and it has a derivative in it. So in prime notation, that would be 2y prime plus x equals 2y plus 1. All right, we'll do one more here. We'll kind of go a little bit bananas, and we'll do something like this. We'll do 3 d2y dx2, otherwise known as the second derivative, plus maybe 2 dy dx. And then we'll go minus 4 equals 0. Okay. Again, it's a differential equation. Why is it a differential equation? Well, because it's got an equal sign, and now there are derivatives in it. Not just the first, but the second derivative. Still called the differential equation. In prime notation, you probably could guess what it would be. It's going to be 3y double prime plus 2y prime, and there was no x or y in this one, so just minus 4 equals 0. Okay. One other note about differential equations, a lot of times we talk about the order of a differential equation. So the differential equation on this first row here, they would be what we call of order 1. These guys here would also be of order 1. These guys here would be of order 2. Can you figure out how to find the order of a differential equation? Give you 30 seconds. Go. All right, time's up. So basically, it's the highest derivative that the equation contains. So if an equation has a second derivative in it, and that's the highest derivative, we call that an order 2 differential equation. If an equation has just the first derivative, and that's the highest one in it, we call that an order 1. So nothing too crazy there. All right, so now what do the solutions to differential equations look like, right? Because that's kind of interesting, and I feel like I should discuss that before we actually show you how to solve them. So what if I said this? Let's back up for a second and transport ourselves to 6th grade. What if I said, show that x equals 2 is a solution to 5x equals 10, right? So if I asked you to do that, show me that x equals 2 is a solution to that equation, what would you do? Well, hopefully you would say you would substitute. You're basically going to take x equals 2 and you're going to chuck it into the equation where you see x, right? Pretty simple. It's basically doing a check, so to speak. So you would get 5 times 2 and say, hey, does that equal 10? Well, 5 times 2 last time I checked is 10, so 10 equals 10. So bam. So you showed that x equals 2 is a solution to 5x equals 10. All right. Well, now fast forward to AP Calculus. Now I might say something like this. Show that y equals e to the 2x is a solution to the differential equation. And then I'll give you one here. dy dx minus y equals e to the 2x. How would you do it? Well, you do it the same way. Now, one thing you might notice, though, is that your answer here to this differential equation is not like x equals 2, right? It's a function. So this is a clue that solutions to differential equations are going to look like functions or maybe relations, right? Things that have x's and or y's in them. So you're like, well, how would I do it, though? How would I show that this is a solution to this? Well, you do it the same way. You're going to kind of chuck it in, but I guess it's a little bit more complicated, right? Clearly, you're just going to chuck in y there because that's what y is equal to, okay? But here, you have to do the derivative of this and put that in there. So you actually have to do the derivatives when you do the check. So if I go to do my check here, right, dy dx, what is the derivative of e to 2x? The derivative of e to stuff is going to be e to stuff times the derivative of stuff, which I'll just put that in front, right? Then it would be minus, right, just y. So y is right there. Well, what is y? Y is just going to be e to the 2x. And then we're checking to see, do you equal e to the 2x, right? We're not sure. Well, 2e to the 2x minus 1e to the 2x would just be e to the 2x. So this, in fact, is a solution to that differential equation. So here you have an order 1 differential equation, and you have a solution that looks like y equals e to the 2x, okay? So you check it just like you check 5x equals 10. So no sweat there. All right, so let's do this now. Let's kick it up a notch, and let's do show that y equals e to the 2x plus 3e to the x is also a solution to dy dx minus y equals e to the 2x. So what are you looking at here? Well, this is the same as the last problem. This is the same exact differential equation, but this doesn't look the same. So now that's letting you think that, oh, maybe there is more than one solution to these differential equations. So, all right, let's do it. Let's check it. So the first thing I have to do in my check is I have to, right here, when I'm doing it, is do dy dx. So when I go to check here, let's do it. Let's do dy dx. So the derivative sum of the derivatives, the derivative of e to the 2x, we just did that before, e to stuff times the derivative of stuff, right? Plus you have constant times a function. So the derivative of that is going to be constant times the derivative of the function. So what's in green here represents dy dx, the derivative of that. Okay, then I'm going to go minus y now. Now, what is y? Y is all of this. So minus e to the 2x plus 3e to the x. So now this is wrong if I leave it this way. So what's the issue here? Duff? Yes, exactly. You need parentheses here, right? So it's minus all of y. So those need to be there. And then it's going to be now, are you equal to e to the 2x? So let's check it out here. So you're going to get 2e to the 2x, that's nothing, plus 3e to the x. But then here I'll distribute the negative. Minus e to the 2x minus 3e to the x. Does that equal e to the 2x? Does anything good happen? Well, it looks like these guys are summing to 0. They're going to cancel out. And then I'm left with 2e to the 2x minus e to the 2x. And yeah, that is actually going to equal e to the 2x. So that's kind of interesting now, because now we basically have two solutions to this differential equation, right? So if I kind of just summarize that now, if you were given the differential equation dy dx minus y equals e to the 2x, you haven't figured these out on your own, right? But I gave them and said, check to see if they worked. Some solutions were, the first one was, I already forgot. Let me go back to it. The first one was, actually, yeah, y equaled e to the 2x. So that was one. But then the next one was y equaled e to the 2x plus 3e to the x, right? So those were two solutions. So my question to you, are they the only two solutions? All right. Are those the only two ones that exist, or are there more? All right. And this is kind of a tough question to ask after only giving you two problems. But I guess your hint would lie in if we go back here and we look at this thing that we added, right? So if we look at this term that we added here, let's pull out this pen. All right. Let's actually change the color. Let's make you purplish. All right. So if we look at that, right, this thing here that was added, how did it play out when we took the derivative of it, or when we checked it in this equation? Well, the derivative of it was just that. It's just 3e to the x. So it's here. And then when you subtracted y, it got subtracted out here. So it actually looks like that any term that fits this kind of format, constant times e to the x, is basically going to cancel out. when you go to check it, because the derivative of k e to the x is k e to the x, and then when you go to subtract y, you're going to get minus k e to the x. So I don't know if that's the greatest of explanations, but basically what I'm saying is that these aren't the only two solutions, right? You also could have y equals e to the 2x plus 3. Actually, that is 3. 32 e to the x. Or you could have y equals e to the 2x plus 5 e to the x. Or we can go bananas and do y equals e to the 2x minus e to the x, right? Minus 1 e to the x, where your constant's negative now. It's still going to work, right? And you're like, well, this one looks weird. This one actually kind of fits this mold, right? You can view this as plus 0 e to the x. So what we would call each of these individual solutions, we call them particular or specific solutions. But it turns out that there's something called a general solution that kind of fits all of these. It's like the mold to create these. And could you guess what the general solution might be? You can hit pause and take 30 seconds. All right, so if you guessed, hopefully you guessed y equals e to the 2x plus k e to the x, where k is just some constant, any real number, okay? And that is called your general solution, where k is just some real number right there, okay? Positive, negative, whatever. So that's your general solution. So now just to recap, a differential equation is an equation that has a derivative in it. And even though I haven't told you how to find the solutions yet, I did tell you how to check the solutions. You basically just plug it in and compute the derivative and simplify the algebra. All right. And then maybe the major takeaway is that when we do eventually learn how to solve these things, right, we're going to get something called a general solution. It's basically a family of functions differing by a constant that will satisfy, in other words, work in or check in this differential equation. And then so you might be saying, well, how do you get specific ones like this, particular solutions? In order to get that, I would have to give you additional information like a point or an initial condition, as it's often referred to. Okay? So that's where we're going to start with differential equations. I'm not even going to show you how to solve them yet. I'm going to keep this video super, super short. All right? So what I'm going to want you to do for homework is kind of basic here. All right. I'm just going to ask you to the following: show that the given y equals f of x is a solution to the given differential equation. And I don't have to post answers to this because if it works, they're all going to be solutions. So it should check. If it doesn't check, then you're no good. All right. So here we go. So we'll go y equals, let's see, 2e to the 1/3 x cubed. That's the given y. Show that that is a solution to the differential equation dy dx equals x squared y. So that'll be question 1. Question 2 will be confirm that y equals 1/4 x to the 4th plus 2 cosine x plus 1 is a solution to, check this out, y prime equals x cubed minus 2 sine of x. All right. So now this might be freaking you out because you're like, oh, it's y prime, but it shouldn't freak you out, right? Y prime is just the derivative of y. It's dy dx, okay? So remember, they mean the same thing. It's just two different styles. All right, so that's it. Those are your 2 homework questions. Homework. So do this and submit it into your folder, and let's call the file, we'll just say sol to diffie q. All right, so call your file that, and then underscore whatever your last name is. Put that in your folder. And that's it. Have a splendid day.